So today I'm planning to tell you more on classical limit of the model with holomorphic polynomials of Z0, Z1. So let me remind you that it was a model where we have the space of states V, that is a space of polynomials of degree n of Z0, Z1. V is a Hilbert space. It means that it is Hermitian space with the metric P. I'll write it like this. In this metric, Zi d over dzj, Hermitian conjugated is Zj d over dzi. Thus, we have four operators, Hermitian operators. Z1 d over dz1 plus z0 d over dz0 equals to n, since it's an Euler operator. And also operators, okay, I'll put n here. And also operators z1 d over dz1 minus z0 d over dz0 that I'll call operator T3. Actually, I would like to change normalization a bit. I want to consider such operator. 1/2 that I'll call T1. And the third one, and here I put I. Now, in physics, they are called spin operators, spin or momentum. One can show it's kind of computation that T1 square plus T2 square plus T3 square equal to, in physics, people use J, that is n over 2. Now, we also introduce operators TA classical, that is TA divided. Okay, so the question is how to divide. So probably it's better to divide not by n but by j. In this case, one can show that TA TB classical is I divided by j epsilon ABC TC classical. So when j is going to infinity, it's n going to infinity, the algebra A tends to commutative algebra with generators xa such that x1 square plus x2 square plus x3 square equal to 1. This is a sphere S2. It is interesting to note, it is interesting to study how points on this S2 appear. To do this, let me recall the concept of dispersion of a stochastic observable O. Dispersion of O equals average of O squared minus average of O squared. If observable is not stochastic, then dispersion is clearly 0. Now, dispersion of O is strictly positive. Really, O minus average of O squared is positive, and its average is non-negative. It's non-negative and its average is non-negative. It means that average of O squared minus 2 average of O plus average of O squared is greater or equal than 0. So canceling this and this, we get the desired statement. Now, this taking average depends in quantum mechanics on the state over which we are getting the probability distribution. The rule is average of O is the trace, here is O, and here is projector on the state psi, that is psi O psi divided by psi comma psi, where vector psi represents the state that belongs, of course, to projectivization of V. So sometimes people call projectivization of V state. Sometimes people are calling by state vector that represents it. From the formula that I call F, it is clear that result is independent on the length of psi. Now we will look at states of minimal dispersion. I will make a claim. The states are of the form EE. It means that to the image, let me call it psi A. I already used this A. Okay, but you will not mix this A with that A, I hope. Okay, I'll put here alpha. It will be better to put it alpha. It corresponds to the image of the Veronese map. from algebraic geometry. This is a map of CP1 into CPN. This is n minus 1. And this is projectivization of space of polynomial of degree n. Okay. So when I mean minimal dispersion, I mean total dispersion of 3 observables. T1, T2, T3. It means I am interested in the study of T1 square plus T2 square plus T3 square average minus average of T1 square minus average of T2 square minus average of T3 square. Now I am pleased to note that the first object is a number. It is n over 2, n over 2 plus 1. So total dispersion equals this minus So how can I reach it? I am looking for maximal square sum of squares of squares of averages. Consider example. Example 1. N equals to 1. One may show that each state can be transformed by SU2 rotation. It is a symmetry of the problem. To this state. Average of T2 on this state equal average of T1 on this state equals to 0. Average of T3 on this state gives +1 with probability 1 plus -1 with probability 0. It is 1. Sorry, 1/2. So altogether I have dispersion, that is 1/2 plus 3/2, 3/4 minus 1/4, it is 1/2. It is the only possible dispersion. Now, let me consider more complicated example. Example 2. Let me take n equals to 2. And here I will take 2 states. One state would be z1 square, purely state, let me call it state up. Then it is clear that average of T2 on state up equals to average of T3 on state up equal to 0. But average of T1 on state up is 1. So altogether I have a dispersion, total dispersion on the space up equals to, I'm going back to my formula, n/2 n/2 plus 1 equals, that equals to 3 minus 1. So it's 2. Now let me consider the space the state that I'll call up and down. It would be z1 square minus z0 square. Not of the Veronese form. It's not a complete square. So not only average of T1 and average of T2 on the space equals to 0. Also average of T3 on this state equals to plus 2. This is due to z1 square with a probability 1/2 plus minus 2 times 1/2. And this is also probability. And it is 0. Let me remind you how to compute probability. Each operator O would be represented as a product of the eigenvalue. And here I have projector to corresponding eigenspace. This formula means that I have lambda I, and here I have trace, which is sum over I, in order not to. And here I have trace projector on the ith eigenspace, projector on psi, that is sum over I, lambda I, Sorry. So this is the probability. So I put my psi. That was I decomposed my psi. That was z1 square minus z0 square. Z1 square is eigenvector for eigenvalue 2. Z0 square is eigenvector for eigenvalue. So sorry, it was T3, and once I misprinted the value here. It would not change the answer, but I prefer all numbers to be correct. So because of this decomposition, both probabilities, sorry, eigenvalue 1. Are equal and equal to 1/2. Okay. In this way, I computed probability. And I see that dispersion is and total dispersion now is 3 greater than 2. Now let us study large N dispersion of the Veronese state. First, by SU2 rotation, we may put it into Z1 to the power n. Then, so I'll call the state psi up n. So how I'm showing this? Each t changes the degree of Z1. So it produces a state orthogonal to Z1 to the power n. However, of course, it equals n. So now, the total dispersion is once again, I forgot to divide by 2. Minus n over 2 squared. So I am getting n over 2. Now, total dispersion of T classical is total dispersion of T divided by J squared of T classical. It is 2 over n. Okay, I will write it better. Of T divided so here I will comment total dispersion of T. So we see the total dispersion of T classical goes to 0 when n goes to infinity. At the same time, total dispersion of state is z1 to the power n minus z0 to the power n. Total dispersion of T of this state equals its maximal value. And of course, total dispersion of T classical of this state is 1. That is not going to 0. It is clear. Since probability to find T3 classical that equals not n over 2, are equal and such state is far from give a definite answer on the question what are values of almost commuting observables TA classical. Okay, so now we will have a break. And after the break, we will continue with this. I still have to prove that the Veronese states have minimal dispersion. How can I do it? Suppose I have minimal dispersion state. That I'll call minimal dispersion. Then I might study this thing. The average of TA. It is a vector in R3. By SU2 rotation, I may turn it to be along the third axis. I mean SU2 rotation of MD state. Thus, I am looking for maximal T3 average square. It can be only or for states that belong to Veronese. Okay, now I'm making, another claim. Veronese states tend to orthogonal basis in the space of states when n goes to infinity. They don't form such a basis for finite n. Really? There are infinitely many. Of them. While the space is finite dimensional. N plus 1 for finite n. So how can I show it? Consider two states. Alpha naught z naught plus alpha 1 z1 to the power n and beta naught and beta say 1 z1. Okay, I can put beta 1 to 1. I can always put the second state, beta naught z naught plus beta 1 z1 to the power n to z1 to the n by SU2 rotation. Now, scalar product is actually a cosine phi to the power n. So what do I mean by this? Alpha naught, alpha 1 is a two-dimensional here I assume that is a point on the three-dimensional sphere given by this equation. Let me draw this sphere. Taking beta naught, beta 1 equals to 1, produce me the beta vector, or beta point. and this is alpha point. Here I have the angle phi. I am connecting the beta point and alpha point by geodesics on S3. So if I look at this formula, I see that alpha beta is cosine n phi between alpha and beta and alpha. And it really tends to 0 when n is tending to infinity. So what is the moral of this story? The moral of this story is that in the n going to infinity limit, Veronese states behave like points. And we are going from something that is known as fuzzy sphere we are going to ordinary sphere. So I want you to keep this picture in mind. Okay. How can we generalize? Of this example? I can provide the most obvious generalization, but let me consider the important generalization of this example. It's called Hamiltonian reduction. Given a Kähler manifold, Y, with the Kähler form, consider the holomorphic action of the complex Lie algebra. I'll write it like this. Such that it preserves a Kähler form. 1 second. Such that compact part of it. So it means In the example we studied, we had y equals c squared, g corresponding to c star, v was z d over dz, v bar was z bar over dz bar, omega dz bar. V minus v bar was z d over dz minus z bar d over dz bar. Then there are Hamiltonians. HA such that V minus V A bar inserted into the Kähler form give DHA. In our example, Hamiltonian was modulo Z squared. Z naught square thus we may consider so-called Hamiltonian reduction of Y over G, defined as take zero of all Hamiltonians and divide by the action of G compact. In our example, we studied model Z naught squared it was S3 and we divided by the action of U1.
Professor, you write in the bracket that HA, the Hamiltonian, is equal to 0, but
yes,
afterwards you write Z1 squares. Okay,
minus 1. -1. Okay.
Oh, okay. Okay.
So actually, thank you plus constant.
Okay.
So thank you for this command. Choice of the constant or several constants here could give different results. Here I want to prove a simple theorem. Orbits of G non-compact intersect zero level of Hamiltonians at most at one point. Proof. Consider LV, and here I put V non-compact. Apply to Hamiltonian. In this case, we can schematically write what's going as follows. And here we have V I So in the case of, okay, let me show it in the simplest possible case. And I'll generalize later. Here I have V plus VI bar. Then what I have here would be just the metric. GI. Okay, so I need to write it in more detail here. VI. And then you may check that is exactly DH over dy, and here I have dh over dy j bar gi j bar. Probably with a factor 2. And this is strictly positive. So H is monotonous along the trajectory. And thus can intersect the zero level only once. And this could be generalized to multidimensional case. Since I don't have enough time, I just want to give you examples. Are so-called toric manifolds. That are generalizations of projective manifold. Before I give this example, let me tell you why I use this proof. So you may say that Y minus bad orbits that do not intercept divided by G complex equals H equal to 0 divided by G compact. And that's why Y minus bad and that's why people say that holomorphic quotient is given by Hamiltonian quotient. So now I am coming to examples. Let me consider Cn. So simple example is Cn. Okay, maybe I will start with Cn plus 1 divided by C star. Where C star is acting by as follows. All these are multiplied by phase. Then moment map is z naught square plus zn square plus constant or minus constant minus c. So it is convenient to write everything in coordinates ti that are zi moduli square. So ti are positive. So we can write down case n equals 1. Well, that's what we have. We can draw case. So I take this octant with T1, T2. Now we can consider n equals 2 case. In this particular case, I have triangle. So maybe it's better not to draw here lines. I can play with it a lot. In particular, I can change. So let me consider c square with the action of c star that acts like this. Minus I phi. And the moment map it would be z0 square minus z1 square plus, say, constant c. Then in coordinates t0, t1, so probably I should put here t0, t1, t0, t1. So for positive c, I'll have a picture like this. It's a ray. So this is c, and I will have a ray. And let me draw the last picture. Suppose I have c cube. And I have C star acting as follows. With Hamiltonian that equals to Z1 squared plus Z2 squared minus Z0 squared plus C. Now, sorry, I need to draw another picture. Now what happens would depend on the sign of C. So let me put here T naught. Here I put T1. Here I put T2. So for C being negative, or probably I should start with, yes, so let me start from C being negative. The picture would look like this. So I will get this interesting figure. However, for C being positive, figure would be not that interesting. And this is definitely product of two rays. And this is something more interesting. What can I show here? I need to explain how to get a manifold out of this picture. So here I considered only absolute values of these, but they have phases. And now I'll try to draw phases here. To draw a phase, I just draw a circle. And it's interesting that the circle goes down when I approach this line. Here it's a bit more complicated to draw such a circle. But in general, one can draw such a circle or imagine it. Here I can draw a circle. So that's why the line here is C. It corresponds to the ray. The object here is CP1. The object here is CP2. I can try to draw circles here. Different CP1s inside CP2. Now, this product of two rays is clearly C squared. And this more interesting figure corresponds to the following. I can draw circles here. And this is called, all this thing is called blow up of C squared at the origin. Okay, so this was geometrical picture, and it is a kind of classical picture. And I'll go to quantum story related to this picture next time.